And so it begins, section 6.8, the last section. It's pretty short and sweet. Let's do it. Section 6.8, the rational zero theorem. True to its name, section 6.8 is solely about the rational zero theorem. Let's go ahead and get started by reading the key concept. If p of x is a polynomial function with integral coefficients, then every rational zero of p of x equals 0 is in the form of p over q, a rational number in simplest form, where p is a factor of the constant term and q is a factor of the leading coefficient. Now, let's unwrap this a little bit. It says that if you set the polynomial equal to 0, then every rational zero, rational as in not irrational like the square root of 2, or not imaginary like 3i, if it's rational, it will terminate, or it will be a repetitive, repeating fraction. It will be found in the form of p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. Then they give us this example, and they say here's a polynomial, here is our constant term, and here is our leading coefficient. So 4/3 could be a 0 because 4 is a factor of 40 and 3 is a factor of 6. Now I think that they chose very large numbers, and I just want to show you what I think is a more practical example. If you had x squared minus 5x minus 14, and you were setting that equal to 0 and you were looking for the zeros. Now certainly you could factor this, but what the rational zero theorem is saying is if you take the factors of the constant, which are 14 and 1, and if we take a plus or minus 1 because we don't know, or plus or minus 1, also plus or minus 7, plus or minus 2, and you put them over in fractional form, the factors of the leading coefficient, which in this case are just 1, then if there is a rational zero, it will be located either at 14 over 1, or negative 14 over 1, 1 over 1, negative 1 over 1, negative 7, positive 2, or negative 2. Those are all the possible locations of any rational zero for this function. And I got them by taking the factors of the constant and dividing by the factors of the leading coefficient. There are fewer choices here than if you use 40 and 6. I just thought it would kind of clarify. Let's move on. So again, if you take the factors of the constant and you divide by the factors of the leading coefficient, you get any rational zeros that might exist. Now some of them won't be rational zeros, but if there is a rational zero, it will be in this group of options. Let's look at f of x. f of x, we have factors of the constant are 3 and 1. Now plus or minus, because it could be a positive or negative, we don't know. And then the factors of 2 are 2 and 1, so we could put in either of these over 2, or we could put them over 1. So what are our choices? Our choices for rational zeros are 3/2 or negative 3/2, 1/2 or negative 1/2, 3 or negative 3, and that's it. I made a mistake, didn't I? Let me just erase this mistake. This should have been a 1. A 1 or a negative 1. So those are our choices for the locations of the rational zero. Now if I didn't have a calculator, what would be an easy way to check An easy way to check would be to use polynomial long division, not polynomial long division. How about synthetic division? Or to plug them into f of x and see if I get a 0 when I plug them in. Or if I'm using synthetic division, when I divide, I should have 0 remainder. Now, in this kind of a problem, you might say, well, that's all well and good, but wouldn't it be a lot easier to factor it? Yes, in this case, it would be a lot easier to factor f of x. This is a pretty factorable function. If we factored it, you'd have to take, let's see, 3 and 1, x and x. I need my middle term to be -1. So I would put my 2 here. And I need it to be negative, so I'd make that negative and this positive. And so you can see I have a 0 at -1, and I have a 0 at +3/2. However, if you look at g of x does not factor. But it does have some very nice zeros. Now we wouldn't necessarily know that, but if we take the zeros, if we take the factors of 10, which are 10 and 1, and 2 and 5, and the factors of our leading coefficient are all just 1, so we would be dividing by positive and -1, which means we'd end up with 10 over 1 or -10 over 1, 1 or -1, 2 or -2, 5 or -5. Those are all the numbers we would have to try to find out if they had a rational 0 for these functions. So at this point, you would try g of 10, g of -10, g of 1, g of -1, g of 2, g of -2, you get the idea, and see if it equals 0. And if you're trying 10 or another large number like that, it might be easier to do synthetic division, where you would say, okay, I need a remainder of 0. When I do this, I get 10, add, I get 6, 60, 53. Oh man, I am not going to get 0. So 10 is not one of the zeros of the function. I can cross that off the list and try another one. And eventually you would try these and you'd either know that you have some rational zeros or you don't. Here is their example. They list all the possible rational zeros of each function. And notice that they took the factors of 16 and listed those first, right here. And then here's the factors of the leading coefficient. Now there are a lot of different options when you take all of the factors in the first group and you divide by all the factors in the second group, and here they are. And so those would be all of the possible values of P over Q, or all potential rational zeros. If there is a rational 0 for this function, it will be included in that list. If there's not, then you'll know after you try all of them. For B, again, you can see this one's a little easier because the constant is 12, which gives you all these, but Q is only 1. So basically, just the positive and negatives in the first list are the ones that you would try. Having a leading coefficient of 1 makes this a lot easier and more practical to use. Here is the check your progress problems. You're supposed to list all the possible rational zeros for each of these polynomials. Pause the video, give it a try, and I think you just make the list. You don't have to actually try them. Good luck. Here are the results for the check your progress. all of the possible locations of rational zeros. Notice that on 1b, since you're dividing by 1, you don't even really have to write it as a division. It would just actually be the factors of 24 because you're dividing by 1. Real world example 2, finding rational zeros. Adam is building a computer desk with a separate compartment for the computer. The compartment for the computer is a rectangular prism and will be 8,019 cubic inches. Find the dimensions of the computer compartment. Let x equal the width, x plus 24 equal the length, and x plus 18 equal the height. So, the volume is length times width times height. We multiply what they've given us together to equal the volume of 8,019. And we multiply this polynomial part out. Then we subtract over the 8,019. And now we need to know where the zeros are. Now, we can make a long list of zeros. First of all, this is not easily factorable, so this is one that you might use them with. And then you also have to be practical. If you are adding 24 and you are adding 18, then probably, you can cut off from about here down. I'm just guessing here that all of these would be too big. Also, you're not going to need any of the negative ones because you wouldn't have a negative length. And one of the width is just x. So if you were to try the positive values from here and work your way up, which is what they did down here in the table. They tried p of 1, and when they did, they got not 0. P of 3, not 0. P of 9, 0. So 9 is the solution. And 9 is the width. 9 plus 24, or 33 inches, is whichever one that was, the length. And 9 plus 18, or 27, is the height. So this is a good example of when you might use the rational zero theorem. Here is the check your progress problem. This is I apologize for the poor picture here. This is W and this is W plus 1. It's evening and it's very difficult to take pictures with my iPad under the light. I get a lot of shadows and things like that. So you cannot see the other side. This side over here is W minus 3. There we go. Now it's all in there. So we've got W, W plus 1, and W minus 3. Go ahead, pause it, and try it. Here's the answer to the check your progress. You set up the equation, possible zeros. Notice I didn't list them all. 1 divides into it. Just a minute, I'm going to change my color there. 1 divides into it. 2 does because it's even. The rule for 3 is if you add up the digits, 1 plus 0 plus 5 plus 6, that equals 12. If the sum of the digits is divisible by 3, then the number is divisible by 3. Also, the same is true for 9. If the sum of the digits is divisible by 9, then the number itself is divisible by 9. 12 is not divisible by 9, so notice that 9 is missing from my list. 4 is if it is even twice. So if you divide it by 2 and then divide it by 2 again, then 4 goes into it. 6 is if it's divisible by 2 and 3. 8 is if it's divisible by 2 and 4. And then 11, I had to check with my calculator, quite frankly. 12 is from 6 and 2. 16 is from 2 and 8. And I stopped there just because I figured it wasn't going to be any bigger than that. I tried 11 just out of sheer luck and got a remainder of 0, and that's how it goes. So I hope you had good luck too. Example 3 is a little bit different. It's about finding all zeros, and you can see it's a nice big long polynomial. And oh my word, here's the list of possible rational zeros. And so they try a couple and they find out that 2 is a rational zero. So they divide 2 out of the original. So if you take 2 and you divide out 5, -8, 41, -72, and -36, then your result is right here, 5x to the third plus 2x squared plus 45x plus 18. From here they went ahead and factored by grouping what was the greatest common factor and the greatest common factor, and they got these two, and then they solved each of those to get the other zeros. So there is a rational zero at 2, a rational zero at -2/5, and then 2 imaginary zeros at 3i and -3i. So go ahead and try the check your progress. I kind of want to show you 3a before we do 3b. I went ahead and found that h of 2/3 was 0, and I divided that out, which left me with this, which I then factored and found the rest of the zeros. You, of course, may have done it differently, but I hope it's making some sense to you. I'm going to now pause and do 3b. Here are the answers to 3b. F of 1/2 equals 0, f of 2 equals 0. I found this out by putting them into my table in my calculator. It seemed like the quickest way to do it. Then I divided those out. Ended up with, after dividing those out, 2x squared plus 18. Solved that, set it equal to 0, and got that x squared equals -9, x is plus or minus 3i. And that ends this section. It was pretty much one topic, so I hope it was helpful. See you soon. Bye-bye.